Our next panel, we're going to end up skipping our break because of timing. Our next panel is on adjuvants. And I'm going to ask the members of the panel that are here to take the stage. Adjuvants can help scientists broaden and improve an immune response. As such, this helps vaccine developers when working on preventing complex pathogens like HIV, COVID-19, and flu. Adjuvants can also help to make vaccines more effective in certain people, like a baby or an older adult. In this session, our speakers will share thoughts about overcoming current vaccine limitations and valuable insights on using adjuvants for future research and development. I'd like to welcome our presenters for this panel. Dr. Prabhu Ananchalam from Stanford University will be presenting on Zoom. And in the room, we have Dr. Kentner Singleton from the National Institutes of Health and Dr. Christopher Fox from Access to Advanced Health Institute. Dr. Ananchalam, your slides are up. I see you on the Zoom. You have the floor.
Hello, everyone. Hope you can hear me. If not, do let me know. Yes.
You're loud and clear.
Great. My name is Prabhu Arunachalam. I'm a senior scientist with Professor Bali Palendran at Stanford University. Thank you for inviting me to talk here today. So I'll be talking about some emerging concepts in the science of vaccine adjuvants. So before I go into the details, could you move to the next slide, please? What is an adjuvant? An adjuvant is a substance that you add to vaccines to improve the magnitude, breadth, and durability of immune responses. To explain that with an example, here's a piece of data from the paper published 2 years ago, where the authors administered humans with a COVID-19 antigen that they developed. On day 0 and day 21, they gave 2 doses of vaccine and measured neutralizing antibody response in serum at the time of vaccination and 21 days after prime and booster, 21 days after the first and the second dose. And these neutralizing antibodies are really critical for protection against infection. Now you can see on the right what happens when humans were administered this. When there was no adjuvant, there was hardly an induction of neutralizing antibody response. As you can see here, between day 0 and day 42, there's really 1 or 2 people that had any detectable response. In contrast, when an adjuvant was added, whether it was adjuvant 1 or adjuvant 2, you had 100 to 1,000-fold increase in the magnitude of immune response. And this is exactly what an adjuvant does. But now in the next 5 minutes, I'll talk about how adjuvants are also known to improve durability and breadth of immune responses, in addition to improving the magnitude of response. Next slide, please. So for that, I have to introduce this idea of how live viral and bacterial vaccines come with endogenous adjuvants. If we think about the development of adjuvants, since Alexander Glennie first discovered that alum has an adjuvant effect in 1920s, there was not really any new approval of adjuvants until 1990s. The major reason, there were several reasons, but it's important to understand during this period, humans have been administered many doses of live vaccines, and many of them have these endogenous adjuvants. And what do I mean by endogenous adjuvants? These are molecules that the virus or bacteria contain, and that can target innate sensing pathways. The major pathways, an important family of pathway is this toll-like receptor pathway. For example, yellow fever vaccine activates multiple toll-like receptors, and this was tested in mouse by Bali's group earlier on. Similarly, if we can click twice more, yes, BCG also activates multiple toll-like receptors and also other surface receptors expressed by dendritic cells and major important cell types. And the inactivated influenza vaccine has also been shown to activate TLR7 and MyD88 pathways. Now, what do these live virus vaccines do, especially something like yellow fever, is known to induce very highly durable immune response that goes on for 3 to 4 decades. You still see serum antibody responses. So based on this idea, next slide, please. Bali's group asked, can we make a synthetic vaccine that resembles a virus, for example, make a nanoparticle that is approximately the size of virus, about 100 to 400 nanometers, and encapsulate these particles with one or a combination of TLR ligands. So in this particular study, what they did was to encapsulate an antigen. It's an experimental antigen called a albumin with a TLR4 ligand or a TLR7 ligand or a combination of TLR4 and 7 ligands. And what they asked was whether this combination antigen plus adjuvant can now improve the immunogenicity of the vaccine. And indeed, the answer was yes. But in addition to improving the magnitude of response, what this combination adjuvanted vaccine did was to improve the so-called bone marrow plasma cells. Now, these are really long-lived cells, and these are the cells that secrete antibody that you measure in serum. So what this study showed was that by activating multiple TLR pathways, you're able to induce specifically this bone marrow plasma cells that in this particular experiment survived for about 550 days in mice, as long as the life of a mouse. So what this tells us is that adjuvants that induce such long-lived plasma cells are really important to induce durable immune responses. Next slide, please. So Bali's group has been working on this to identify such adjuvants for a long time, and in collaboration with many industry partners, including 3M, IDRI, and AAHI, with Chris Fox here, we have identified this molecule called 3M052, which is a TLR7/8 agonist that induces such long-lived bone marrow plasma cells. So here is a non-human primate experiment where similarly they tested multiple adjuvant combinations. And as you can see here, when you give the traditional old alum, you do see antibody responses in serum. But when you look at this particular bone marrow plasma cells, which is what maintains the durability of response, there was hardly an induction. In contrast, when you see a molecule like 3M052, it really induces bone marrow plasma cells that survive in the system for about a year after vaccination. And we haven't tested beyond this. Let's go to the next slide. I'm going to slightly shift gears and talk about what alternative pathways can adjuvants target. And I just mentioned that toll-like receptors and dendritic cells are an important, component of what adjuvants target. But clearly, what we are also learning is adjuvants can work through other pathways that are beyond dendritic cells and toll-like receptors. And this primarily comes from study of recently approved adjuvants that includes MF59 and ASO3. These are squalene-based emulsion adjuvants. And what is known about them tells us that you don't typically require toll-like receptor activation for immunogenicity of these adjuvants. And data also do not really show a direct sensing of these molecules by dendritic cells. And we still do not exactly understand how these adjuvants work, but these adjuvants are really potent. And I'll show you in the next two slides an example of that. Next slide, please. So here is a study that we did 2 years ago, where we tested which of these 5 adjuvants, which included 2 oil and water emulsion-based adjuvants and 2 TLR-based adjuvants, and compared that with the traditional alum adjuvant. We asked the question, which of these would best adjuvant this RBD I5350 nanoparticle antigen developed by Dr. Neil King and David Wiesler at the University of Washington? And what we found, next slide, please, was all these adjuvants, especially ASO3, AS37, CpG alum, and alum, induced really high autologous neutralizing antibody responses. That is, neutralizing antibodies against the vaccine strain that was immunized with. Next slide, please. But when we looked at the breadth of immune responses, and what we are measuring here is neutralizing titers against the beta strain, and at that time in 2021, this was the most immune evasive strain. What we saw was clear differences between adjuvants. For example, as you can see here in red, ASO3 induces quite good neutralizing antibodies that target the beta strain. Whereas when you look at something like AS37, which is a TLR7 agonist, but still the breadth of the response was relatively lower, suggesting that adjuvants can differentially induce the breadth of immune responses. Next slide, please. We further went on to show that adjuvanting this RBD I5350 nanoparticle antigen with ASO3, which was eventually approved for clinical use in South Korea, induces very high magnitude of broadly neutralizing antibody responses that was able to neutralize SARS-CoV-2 and its variants in up to BA5 at that point, but also really distant variants such as really distant viruses like these bat viruses, SHC014, WIV1, and so on. Even some of these animals induce neutralizing antibodies that can target SARS-CoV-2 for up to 6 months. So I just showed you that adjuvant like receptors can also induce highly potent and broad responses. In the last 2 minutes, I'll indicate what are those other pathways that we can target. Next slide, please. So the first one is all well-known immune pathways, for example, cytosolic pattern recognition receptors. Alum has been shown to induce the NLRP3 inflammasome pathway, which could also be targeted. And cytosolic RNA receptors, for example, the Pfizer-BioNTech mRNA vaccine is sensed by MDA5 to induce CD8 T-cell responses. Similarly, C-type lectin receptors. These are receptors that are expressed on multiple innate immune cell types. Their functions has been relatively poorly understood, but now adjuvants that are targeting some of these molecules like MINCL has been showing really promising induction of specialized T-cell responses. And T-cell responses is an area where adjuvants have relatively been exploited less. Next slide, please. The second pathway is the tissue damage. In addition to inducing innate immune pathways, you can actually use cell death and tissue damage to develop adjuvants. For example, this molecule MF59 that I briefly introduced previously does not require TLR-mediated signaling for its immunogenicity. However, the release of ATP from the muscle, especially from dying cells, seem to be critical for its immunogenicity. Next slide, please. And it has been known for a long time that there are specialized dendritic cells that take up dying cells and induce CD8 T-cell responses through a process called cross-presentation. Whether some of these adjuvants, access that by inducing specific cell death is something that the field has been, quite intrigued by. And in fact, an MF59-like adjuvant called Adjuvants, Bali's group had shown that induces a specialized cell death called necroptosis, and this is required for the CD8 T-cell responses elicited by this adjuvant, at least in mouse. And lastly, next slide, please. We are also learning the high interconnectivity between cellular metabolism and immune responses. Are we able to use small molecule modulators of metabolism, something like Memtor, something like rapamycin that is already used in clinic for other reasons? Can we also use them as an adjuvant is interesting. And at least in mice, we are able to see that it could be potentially used to induce especially CD8 T-cell responses. And more recently, this was also tried in kidney transplant patients in humans, and it does show a functional improvement of T-cells elicited in the presence of rapamycin. Next slide, please. So in summary, what did I show was adjuvants, in addition to promoting the magnitude, do improve durability and breadth of immune responses. And adjuvants that induce long-lived plasma cell responses are really key to improving durability of immune responses. And there are novel pathways such as cell death and metabolism that can be targeted to induce CD8 T-cell responses. So with that, next slide, please. I thank you for your attention, and I would like to acknowledge all the people without whom I would not have been able to present this work here. Thank you, and I'll be happy to take any questions later.
Thank you, Dr. Runchalam. A very enlightening presentation. Our next presenter is Dr. Kentner Singleton from the National Institutes of Health. Dr. Singleton, your slides are up. You have the floor.
All right, thank you very much. So, as I mentioned, my name is Kentner Singleton. I work at the National Institutes for Allergy and Infectious Diseases at the NIH, and that's where I run the vaccine adjuvant development program. So what I'm going to do for the next few minutes, I'm going to give you a very high-level and whirlwind tour of some of the products and strategies that are being conducted within the vaccine adjuvant field to improve vaccine efficacy. And so about 20 years ago, we realized at NIAID that when people were developing vaccines, they're really highly focused on that antigen component, and there was very little attention being made on the development or discovery of vaccine adjuvants. And so because of that, we created this solicited program to facilitate that research. The program here is antigen agnostic, and it's really built along these 4 goals that are on this slide. The first is the discovery of new vaccine adjuvants to feed the pipeline and to really evolve with the science as it's been moving forward. That's also for exploring combination adjuvants, as you heard in the previous talk, which are critically important for mimicking what we see in natural infections. For supporting basic research to understand how vaccine adjuvants can work and how we can rationally select which adjuvant should be used to really maximize the effect of the vaccine depending on the target of that vaccine and the goals of that vaccine. Support the preclinical development of these vaccine adjuvants. That's the IND enabling activities that is needed to get these into the clinic. We also support head-to-head comparison of these vaccine adjuvants, again, to better understand which vaccine or which adjuvants should be used within which given situations and the goals of the vaccine. And finally, there's no point in supporting the discovery of a vaccine discovery and development of vaccine adjuvants if people don't know that they exist and if they don't have access to them. All right, so this slide really gives a high-level overview of some of the targets that we have supported through our program. You can see in the upper left that we have supported vaccine adjuvants that target a number of the receptors that were described in the previous talk. Many of those adjuvants are synthetic molecules. This is a result in some ways because they come from high throughput screens. Also, synthetic molecules make it very easy to manufacture, so you can manufacture them at multiple different sites in a pandemic situation to increase supply. It also makes them amenable for formulation activities because you can do structural modifications. We also have natural compounds within our portfolio, protein adjuvants, for examples, and also peptides, squalene, and saponins as well. There's been a concerted effort within the field to make mimics or alternatives of existing adjuvants that have been successful within the field, but that might not be available to the vaccine development community. QS21 is a very successful adjuvant. It's developed isolated from the bark of squalene or of koala trees. And so people had developed semi-synthetic or fully synthetic versions of QS21. We've also looked at congenitors of QS21, so other components from that tree that can be used as vaccine adjuvants, and also alternate sources such as yeast-derived and other plant-derived QS21s or QS21-like molecules. Same with squalene. MF59 is a very successful adjuvant, and we have supported the development of other alternate sources to get either chemically identical squalenes to MS59, or of course exploring other squalenes from plants or other animal sources. As you heard in the previous talk, there's a lot of attention on the combination adjuvants such as TLR4/7/8 agonists. Also, AS01 is a very successful combination adjuvant composed of QS21 and a TLR4 agonist. And so we have programs that developed very similar adjuvants to that highly successful AS01. And other adjuvants that we've supported are, of course, oil and water emulsions, LNPs, and interestingly, outer membrane vesicles. These are little blebs that have come off of bacteria. The body sees that as an active bacterial infection. So what we could do is isolate those outer membrane vesicles. We can either admix them with an antigen, or you can engineer them so that they express the antigen agnostic or on that OMV. So there's been a lot of attention on the development of adjuvants for intranasal and oral use to elicit that mucosal immune response. DMLT has been used for oral vaccination efforts for enteric diseases. We're also supporting the development of a TLR agonist in sublingual biofilms that can, some of the advantages there is there can be easily distributed, so you don't have the cold chain issue that you might have with some other the traditional vaccines, and also for ease of administration in a needle-free environment. Intranasal vaccines, of course, are very important for respiratory infections. There's been a lot of work there on oil and water nanoemulsions, where there have been several clinical trials within that space, particularly for influenza, and also for TLR agonists, as you can see here, TLR 478 agonists and CpG. These can be administered either by a spray, or they can be freeze-dried or lyophilized and put in blister packs, which again helps with the cold chain issue and distribution to LMICs, and then administered intranasally. I want to mention very briefly about some advances in vaccines to help treat allergic allergy and also autoimmune disorders. NEO1 is oil and water nanoemulsion from Blue Willow, and it's being used for oral vaccine to treat peanut allergy, and this is entering clinical trials relatively soon. And then you also have TLR 4 agonist, a small molecule that's being given intranasally to do, again, immune deviation to treat allergic rhinitis. And what's really interesting about the allergic portfolio is the information we gain from this allergy portfolio will also inform our development of vaccines to treat infectious diseases. So, for example, I was talking about to treat allergic reactions, you want to do that immune deviation from a Th2 to a Th1 response. Well, that's something we're also very interested in from an acellular pertussis vaccine, which can elicit a Th2 response. And for perhaps a booster, we want to shift that more to a Th1 response. All right, so fine-tuning of adjuvant effects, we call this adjuvanting the adjuvants. You heard a little bit about this in the previous talk. These are compounds with no immunostimulatory activity themselves, but they can modulate or enhance adjuvant activity. So this could be an mTOR agonist or antagonist, or an NF-kappa B antagonist or agonist. And there was a really nice paper published by Aaron Essercon very recently, where they conducted a high throughput screen of multiple kinase inhibitors, and it showed that you can really tweak the immune response to a vaccine. So in the upper right corner here, you can see with CpG, if you add, you can see one of the slides anyway, you can see that if you add different compounds, you can either upregulate or decrease the TNF-alpha response, and you can also completely abrogate the IL-6 response. And so this is important because it could be a tool to really reduce that reactogenicity that we see in some vaccines. In the lower left, this is a work by Dr. Dennis Carson and Tomoko for it's a 2E151 is a molecule that, when added to a TLR4 agonist, really boosts the efficacy of those vaccines. All right, so RNA vaccines are really hot at the moment. It's really been a really exploding technology, and I really think has changed the landscape of vaccines, of course. There's been discussion about whether or not you can add adjuvants to RNA vaccines to boost that the efficacy there, particularly for the T-cell response. And a lot of people have waved that off. They said, well, if you do that, you're going to inhibit the translation of that RNA into that protein antigen. But what we've found in our program that that's not the case. In fact, you can add adjuvants and really enhance the efficacy of these RNA vaccines. And that makes sense if you step back, because LNPs are adjuvants. They have adjuvant activities, even though we think of them as platform technologies, and different LNPs can induce different immune responses. And so you can lipidate TLR agonists, put them in the LNP, which again acts as the adjuvant, or you can use genetic adjuvants. So on the right slide here, you can see where Dr. David Dowling from Boston Children's Hospital has added an IL-12 RNA to the Pfizer vaccine, and that rescued or enhanced the response of that vaccine in elderly animals. All right, and so this is a case study I think would be really unique to you, and it really shows that the necessity and the power of screening multiple adjuvants in the context of special populations, but also within the context of the different antigens. So this is within the context of creating vaccines to treat opioid use disorder. So we're creating vaccines that target heroin or fentanyl or morphine analogs. And what we found here that when Ofer Levy and David Dowling screened multiple adjuvants using patient population for people who had opioid use disorder, that they were hypo-responsive to TLR4 agonists. So they weren't very responsive to things like MPL. And that was really important as we were developing these vaccines to treat opioid use disorder. Now, further studies in that found that the reason for that is that opioids can bind to and activate or inhibit the TLR4 receptor. And so you had this chronic TLR4 stimulation in these patients with opioid use disorders. And so that's why they became somewhat tolerant to TLR4 agonist. And that also affected how we looked at the antigen, because if you took a morphine hapten and had on a carrier and added a TLR4 agonist in a naive animal, that antigen would actually inhibit the ability of the adjuvant to work. And so addition of MPL just didn't boost the efficacy of that vaccine. And that was work by Marco Pavoni at University of Washington. Similarly, when we did the same thing with fentanyl haptens attached to a carrier, when you put them into, again, opioid naive animals, that antigen actually inhibited the ability of TLR4 adjuvants to work. And because of that, TLR7/8 agonists became the lead agonists or the lead adjuvants for our program. Other work by Kim Janda has shown that CpG also works, and Betsy Norton and Thomas Cosson has shown that DMLT works very effectively for opioid vaccines as well. All right, in the last 30 seconds, I just want to highlight our vaccine adjuvant compendium. This is a database that we created within the last year and a half where adjuvant developers and researchers can put their adjuvants into this online database where the vaccine development community can then access, search, and find vaccine adjuvants for their vaccine development programs. And so if you look at AHI, for example, you pull up a number of adjuvants. If you click on the adjuvant, you get this product sheet. What's really important about this is you get that point of contact of who you should contact to initiate a dialogue to say, hey, can we use your adjuvant for our vaccine development program? So far, this has been incredibly successful with the vaccine development community. It's also being very widely used by NGOs such as Bill and Melinda Gates Foundation, WHO, and CEPE. And with that, I'll just lead you with some resources that we have available on vaccine adjuvants and vaccine development programs. All right, thank you.
Thank you very much. And our final presenter in this panel is Dr. Christopher Fox from Access to Advanced Health Institute. Dr. Fox, your slides are up. You have the floor.
Thank you. It's a pleasure to be here. And thanks, Prabhu and Kentner. I think I'm going to be able to skip one or two of my slides because they covered it so well. So I'm going to skip that one because you know what adjuvants are now and the different types of adjuvant classes. And I just want to add to what Prabhu said about the beneficial attributes of adjuvants. So he covered response broadening and durability in great detail. And I'd like to add to that adjuvants can really make the difference between whether a vaccine works in special populations, whether it's young children, as represented with the table on the lower left here, where a squalene emulsion adjuvant doubled influenza vaccine efficacy, or in the elderly. And on the lower right there is the Shingrix clinical data represented in yellow, where over 90% efficacy was evident even in the very oldest populations tested, and compare that to the previous live attenuated vaccine in blue, which had much lower rates. And then another illustration of the potential benefit of adjuvants is represented on the upper left here, and that is vaccine dose sparing. So in the case of a pandemic H5N1 vaccine, including an emulsion adjuvant allowed greater than 20-fold dose reduction of the vaccine and still maintain equivalent or higher responses, functional antibody responses. So I think there's many roles for adjuvants, and it's really context dependent on when and what type of adjuvant is most appropriate to use. So in my remaining time, I would like to just highlight a few areas that I see as particular challenges and/or opportunities in adjuvant development going forward. There's obviously not time to cover everything in adjuvant development. It's a very complex endeavor, especially to get things to clinical testing stage and then obviously in a licensed vaccine. But there are a few areas that I think we can maybe do better on or just understand why they're important. And so some of these have, again, been touched on by Prabhu and Kentner, but I'd like to just add a little bit additional flavor to what they said. So first off, the importance of formulation. And thanks again, Kentner, for a plug on this. We consistently find that this is underappreciated in the adjuvant and vaccine development conferences. You can't just take any adjuvant, even the oldest and most well-recognized adjuvant, alum, and pair it with any antigen by just mixing and then immunizing and expect to get optimal responses. And unfortunately, that's how many adjuvants are used, at least in preclinical studies, by well-intentioned researchers who are just looking to boost immune responses to the antigen that they very carefully developed. But to really optimize adjuvant activity, you have to take a comprehensive look at all of the physical chemical interactions occurring between the adjuvant and the antigen. Some of those are listed here for the case of aluminum adjuvants, and you can see there's many different criteria that you would take into account. For instance, the isoelectric point of the protein antigen and the surface charge of the aluminum adjuvant. And there are different types of aluminum adjuvants, so you can rationally select an adjuvant that plays the best with your antigen. So understanding these concepts is critical and may go a long way to explaining why in some cases we don't see the adjuvant effect that we expected in early studies. Another important point here is that not every adjuvant is going to work for every vaccine. So for instance, we saw some really nice data with AS03 in the SARS-CoV-2 nanoparticle antigen that Prabhu showed. But that doesn't necessarily mean that that's going to be the best adjuvant for every antigen. And in some cases, an adjuvant that performs not very well with one antigen will be absolutely the best with a different antigen. So it really depends on the context, and you have to take an empirical approach with these questions and really evaluate different types of adjuvants in each case. Reactogenicity was mentioned briefly earlier today, and so a lot of times when a vaccine is reactogenic, people first look at the adjuvant, and that could be with good reason. So for instance, we know that often injection site pain is a common reaction with adjuvant containing vaccines, and there's been a bit of a myth out there, I think, that the more reactogenic a vaccine is, the better immune response that may ensue from that. And there was a recent study that took a real close look at this with the Shingrix vaccine, which contains a potent combination adjuvant, as Kentner mentioned, and is associated with significant injection site pain in many recipients. But when investigators looked at the immune response in terms of antibody titers and correlated that with the pain experienced or reported by the recipients, they saw a very modest effect. There was, it was significant, but it was a very weak association. And in this particular manuscript in the Journal of Infectious Diseases, they concluded that this is not really, reactogenicity is not a reliable marker for immunogenicity or protection. And so, the corollary of that is that we can potentially find ways to reduce reactogenicity attributable to adjuvants through appropriate formulation or dose optimization. And so the very same adjuvant that's in Shingrix, but at half the dose, is used in the new RSV vaccine, Arexvy. And lo and behold, in that reactogenicity profile, we see about a third or a half of the reported events. And so it may be there that the lower adjuvant dose is giving us that preferred safety profile. Okay, I was quite interested in the discussion earlier today about alum and the Th2 versus Th1 paradigm. We do think there are steps that can be taken to improve the old adjuvants like the alums and the squalene emulsions. And so one example of that is what we've developed. It's called nanoalum, and really it's a nanoparticle aluminum formulation with a controlled smaller particle size. And to our surprise, we found that this actually switches the Th2 response typical of alum adjuvants to a Th1 response with a recombinant TB antigen. And another beneficial effect is that it's stable to freezing excursions, which alum is not. And that results in many wasted vaccines worldwide when they're accidentally frozen. And then Kentner touched on this nicely. You know, RNA vaccines, I'm extremely excited about their potential and what they've done for the COVID pandemic and going forward. And I think there are ways to apply adjuvant technology to RNA vaccines. Very recent report showed just that you can encode an adjuvant in the RNA in the upper right there and boost responses. But also, I don't think RNA vaccines are going to answer all of the immune response challenges that we're looking at. So for instance, this is preclinical data, non-human primate model on the lower left, where a protein with an adjuvant, a combination adjuvant 3-MO52-SE, after 2 immunizations and then following the animals for a year, elicited about a log higher neutralizing antibody titers to both the homologous and heterologous strains compared to the same protein encoded in an RNA LNP vaccine. So I think there are roles for both platforms, and perhaps the optimal way to look at this is using them in a heterologous approach, depending on the context and what is needed, where RNA vaccines can be first to address a pandemic response, for instance, but maybe if we're looking at particular populations or locations of immunity, such as mucosal immunity or durability of immunity, adjuvanted protein vaccines still may have a significant role to play there. And then coming back to I really enjoyed the last session on sort of a planetary health perspective on vaccines, and I really believe in that as well and the importance of looking at that. So 2 quick examples of this. One was a clinical study conducted by Dr. Hoff's team at St. Louis University, who's here on the NVAC committee. And we developed an adjuvant-containing TB vaccine that was thermostable. And we did this by combining the antigen and adjuvant in the same vial and then freeze drying it. And we evaluated this, Dr. Hoff's team evaluated this in a phase 1 trial and showed that not only did we maintain the immune response profile of the non-thermostable previous version of the vaccine, but we saw significantly greater immune responses. And then in terms of squalene, which Kentner mentioned, this is for current products is derived from sharks. And we believe there's a better way to do that. And with NIH funding, and working with partners, we've developed sustainable sources of squalene and squalene analogs that work as well, if not better, in preclinical testing. And then finally, just to show that, as Prabhu mentioned, for many decades, the only adjuvant in approved vaccines was alum, different types of aluminum salts. But in recent years, we've seen the regulatory climate improve and allow for many different adjuvants and approved vaccines worldwide now. And I think we can expect this to continue as regulatory bodies become familiar with new adjuvants. And then just to highlight again, the support from funding bodies like NIH, who are making adjuvant access easier and providing support for this kind of work. And the handful of labs around the world that are trying to enable greater access to adjuvants, which has previously been a difficult problem because only very few entities held that technology. And so I think there's good things to come. I'll stop there. Thanks.
Thank you very much. I want to thank all the members of the panel. I knew a little bit about adjuvants, and I think I've at least tripled my knowledge in the course of this last few minutes. We have a question or comment from Melody Butler.
Yes, thank you very much for the presentations. My question is for the first presenter. During your presentation, you were discussing how cell death and rabo was actually indicative of a good immune response. So for me, in hearing that, I'm thinking cell death is going to increase pain, increase swelling. Can you help explain why that would be beneficial if I'm explaining to a patient why the soreness is actually indicative of the vaccine working and being more effective?
Yeah, so the way I explained it is it's mainly how immune cells, specialized immune cells like dendritic cells, are evolutionarily they're taught to take up dead cells, and thus that it promotes CD8 T cells. Now, whether this cell death that I mentioned causes pain in patients is something that's not directly studied, but as you say, it's likely to be a possibility. Now, I would also add, like Chris mentioned, having pain and gain is not proportional, and therefore, we need to understand whether that cell death induces any side effects or any pain that these people have before being able to address the question that you asked. My talk was more on the biological mechanistic side, if that makes sense.
It does. So I'll look forward to a follow-up on your presentation next year.
Thank you.
Daniel Hoft.
Thanks, Bob. And thanks to all the speakers. Really interesting session. I guess my question is relatively simple, but maybe directed against all three of you. And that is, I never understood why Shingrix works better than the live vaccine, since live vaccines in general do tend to work much better than inactivated vaccines. Is it just a simple thing where the virus is over attenuated, there's pre-existing immunity, so you don't really get a take with the live vaccine? And Shingrix gets around that by inducing a response with adjuvant? Or is it something more complex and interesting?
We're all looking at Prabhu to take that one. I don't know the answer to that, Dan.
Yeah, I don't know the answer to that either, but my understanding of Shingrix is that, the virus is hiding in the body somewhere, and it kind of starts showing up when your immune system slowly starts becoming older. And by the time the original immune response elicited by the varicella vaccine or your initial infection could also have been diminished. That's the best I could think of. I do not have any additional explanation, but I can certainly mention that this ASO1 adjuvant used with Shingrix vaccine is quite powerful, and therefore it elicits, it just boosts the response really effectively. And it induces a good response, even in elderly individuals.
Any other questions or comments from the committee members, either in the room or online?
Just a comment that I think
Go ahead, Rob.
Shingrix is the recombinant subunit versus Zostavax, which was the prior live version.
Great. Well, I want to thank the members of this panel. Very interesting presentations, and as you have all told us, we've got miles to go on this issue also, as well as any of the other areas. Thank you again. We've reached the end of our agenda with the exception of our public comment. And I understand we have one person on the call for public comment today. Teresa Rangham, are you on the line?
And Teresa, you may need to dial *6. Teresa, we don't see you or hear you. But you may need to unmute your phone.
I'm sorry, I was listening to the video. Did you call on Teresa Rangham?
Yes, Teresa, we hear you. You are on for public comment. Thank you.
Thank you so much. My name is Teresa Rangham, and I'm the Executive Director of the National Vaccine Information Center. Our mission is to prevent vaccine injury and death through public education and to defend the informed consent ethic in U.S. vaccine laws and policies. Our co-founders worked with Congress at their invitation to draft and pass the National Childhood Vaccine Injury Act of 1986. In viewing today's recommendations from the Vaccine Safety Report passed today, it seems notable that the report appears to have the expectation for the public to comply with recommendations without participation in the framing of the report from a consumer perspective. The agenda of vaccine compliance appears to undermine the human and informed consent right to decline vaccines without coercion and penalty. NVAC also has concerns about the lack of diversity in voices with respect to vaccination presentations today. Where are the healthcare professionals and advocacy groups speaking on behalf of the growing section of the population who have legitimate vaccination concerns? The answer is they've been censored, canceled, and ignored, though vaccine-concerned voices now go far beyond a parent base to include many mainstream healthcare professionals and academics who previous to COVID-19 were your trusted messengers. They now hold many of the concerns that our organization expressed early in our 40-year history. Additionally, claims of responsiveness ring a bit hollow when considering that today's presentations do not appear to be responsive to the IOM 2005 report on public trust in VSD studies. The IOM found in 2005 that the public had legitimate concerns about VSD studies and made recommendations that the data sharing program needed to be improved and data sets opened up to independent researchers to either confirm CDC and VSD partner findings with the ability to audit and pose alternative hypotheses to maintain public trust. Other systems such as CISA that are also used in a similar fashion as VSD for making vaccine safety statements should also be subject to the same scientific rigor by independent researchers. So the big question with regard to responsiveness to public concerns would be which white paper studies have followed the IOM 2005 recommendations and undergone the independent scientific rigor recommended by the IOM. Have these recommendations been similarly applied to other vaccine safety monitoring systems? While this committee doesn't answer questions from public comment, certainly answering these questions with respect to your charge is necessary. Without a diversity of viewpoints in these meetings, independent research, and actual work to build back trust with the public, today's proudly pro-vax presentation and the building confidence presentation equate to little more than one hand clapping in a pro-vax echo chamber. NVAC has advocated for increased vaccine safety and high-quality independent vaccine safety studies. NVAC has been a voice of legitimate vaccine safety concerns for over 40 years and has a history of working with government and has sat on these committees to achieve these goals, while also advocating for vaccine policies and laws to incorporate informed consent principles. The informed consent ethic has guided the ethical practice of modern medicine, born from unethical medical experimentation conducted during World War II. Informed consent protections must be incorporated into all recommendations by the NVAC, or we turn away from the ethical practice of medicine and the ethics requirement for consent to be strictly voluntary and without coercion and penalty. Vaccination is not an exception to this foundational medical ethic. While NVIC supports access to vaccines, trust will not be earned through the silencing of those with concerns or coercion and mandates to accomplish compliance in violation of the informed consent ethic. Thank you for the opportunity to provide public comment today.
Thank you, Ms. Wrangham. We appreciate your comment. Okay. At this time, we do not have any other public comment on the line. We will adjourn for the end of today's session. Tomorrow morning, September 22nd, we will begin at 9 a.m. Eastern Time with our call to order for the second day of our September 2023 NVAC meeting. I want to thank you for your participation to the members of the committee, our liaisons, and our government representatives, and thank all of you that have watched on the webcast. We'll see you tomorrow.
Produced by the U.S. Department of Health and Human Services.